in certain topics that come in week 7 and week 8 specifically, so that we can take. All right. So I hope you remember. I mean, some of you may have seen the week 1 solve with instructor session. So in that session, what we did was we segregated some numerical questions from the course. I mean, the part that we generally ask for week 1, and then created Jamboard for that. I mean, some platform where we can solve and discuss on those questions. The same thing we'll do for this session. I have segregated out around 3 to 4 questions, which I thought should be discussed because this will be helpful for your end term and quiz two also. Okay, so you can just note the questions that we are going to solve. Generally, we would, I mean, I would ask you to solve those questions by yourself, but I guess this time it won't be possible because generally they are doubts. So I don't want to, waste much time in giving you the time and then to solve. So I'll just rather read the question and start solving. After that, if the time permits, we can take some questions regarding week 9. Okay. So I'll just share my screen. Yeah, okay. So I hope you can see my screen. I'll try to zoom in a bit. Okay. So, okay, so I'll start off with the first question. All right. Yeah. So I mean, these questions. So these questions are already taken from practice and graded questions of week 7 and week 8. The graded questions of week 8 I have not taken. The reason being the deadline of week 8 is still yet to pass. So that can come in as a doubt when the deadline is over. Okay, so we can easily discuss those questions probably in the next sessions. All right, but this session I've taken some questions which are mostly belonging to week 7 and some practice related questions regarding week 8 if time permits. You can ask your own question as far as numericals go. All right. So I hope this question was taken earlier in the earlier session, but just wanted to give it one more try so that it becomes pretty clear. As I mean, questions related to this had come in previous quizzes. So I hope if this gets clear and if any questions or any variation of question comes in the quiz regarding to this, we can try to solve. Okay. So I'll just read out the question. All right, so I'll just read out the question. A magnetic disk operating at 7,200 RPM is being used to store data, right? The disk can only spin in one direction at the constant speed of 7,200 revolutions per minute. If the operating system sends a request to the disk controller to fetch the data from the disk, what is the worst case latency in milliseconds before it can start retrieving data? All right, so can somebody unmute and tell me what is that we're trying to ask? I mean, what is this disk? What is this magnetic disk? Why are we trying to fetch data? Or what if we are trying to fetch data? From where does this latency comes? And what is all this? What is the spinning speed and all? Right. So this is what we need to understand in this question. If this is clear, then most of the things will be clear. Okay. So, okay. I'll start by myself because as I said, we will not be, putting in a lot of time. Okay. So what is happening here? So just one. So what is happening here? There is a disk. So just now we have trap charge technology storing like things like pen drive and solid state devices, right? But initially and still the HDDs are still in use, right? So what the basic principle of storing data is a disk that is rotating at certain speed. Okay, and then what happens? So let's say I have a disk, a circular disk that is storing some data, and somewhere in the system there is a small bracket that is called as a reader or the lens. All right, so this disk, it is like a normal VCD or DVD that we see, right? So it is similar to that in looks. So the entire disk stores some data. Okay, the entire data is stored in the form on this disk, it is printed. All right, and then when the disk passes through the reader, it reads out the information, which is with the help of a lens. All right, so this is what is happening. All right, so this is just let me just uh, try to increase what is happening in the reader part. Okay, so this is the reader. Okay, and this is the disk. All right, here. So what happens when a bit of data passes through this reader, it reads it out, and then that data passes from here as the disk is rotating continuously. All right, so there are two things to note here. One is the speed of the disk. Okay, 7200 RPM. By the way, the actual speed of this is this 7200 revolutions per minute. Although both are same, but I mean there can be difference. Okay, what is the difference? In general question, a magnetic disk operating at 7200 RPM is being used to store data. This is the rating of disk. Rating of disk means 7200 rotations per minute or revolutions per minute would be the maximum at which this disk rotates. Okay, at the I mean at the place or at the state when we were trying to read the data, or at this current instant, there can be a different speed of disk with which it is revolving and retrieving data. All right, in our case what is happening, the revolution, rated revolution, and the exact revolution, the practical case of the revolution is same. Okay, the latter one, latter 7200 revolution can be anything less than 7200 also. All right, in that case you just have to ignore this part and use only this part. Why? Because this is a rating, and we need to consider only that case at the instant we are trying to calculate the date, or whatever it is asked in the question. All right, so currently this disk is rotating at 7200 revolutions per minute. All right, so what happens? A data comes from here, goes, so data itself remains on the disk itself. It is just the lens that is on top of it which keeps on reading. Okay, so if the data passes below the lens, it will start reading the data. So let's say if this is 1100101, it will start retrieving like this, right? So 1100101. Okay, so what will happen? Let's say this is the instant where this data just entered or just passes through the lens. Okay, what will happen if my data was here, and at this instant I started reading the data? Okay, so what was the data? 1100101. Okay, so I can say that. So if I just draw dotted lines here, I can see that the instant when my lens started reading the data, some of my data has already passed. All right, so what it will read? It will read in the second case. So this is the first case, this is the second case. So in the second case, what it will read? It will not read, I mean, it has missed 110. So it can read from 0101. All right. And then this is not the actual data. This is the misinterpreted data. Right. This is the case. And then there can be third case where the entire data has passed. All right. So this is third case. 1100101. All right, so the entire data has passed the reader, and then the reader started reading the lens started reading the data. In that case, it will either read nothing, I mean, it will either read nothing, or what is coming here at that instant, right? What is coming, I mean, what the lens can see at that instant, it will start reading that. In either of the case 2 and 3, the data read by the lens will not make sense. Why? Because I want the starting point and the ending point. I want the entire data to be read. Okay. So what will happen in any of these case, 2 and 3, even if a single bit has passed reading the lens, the data, the actual data will be start getting read only after it takes the revolution and comes back to the lens, right? Because here I know that I have missed 2 bits. Here I know that I have missed lot many bits in case 3, but in case 2 I know that I have missed 2 bits. Okay, 2 or 3 bits have been missed. So there is no way I can put a random bits in there or the random information there. It should make sense also. All right. So what this system does is it lets the disk to take the complete rotation and then starts reading when the data is back at position number 1. Okay. Okay, all good. The data is read. Okay. I mean, in all the cases, in with this, we make sure that in all the cases, case 1, case 2, case 3, the data is read correctly. Now, there is one problem with this in the case 2 and case 3. In case 1, whenever the data was about to enter and the reader started reading or the lens started interpreting the data, I got the entire data without any delay, right? So here I can say there was no delay, right? But in case 2 and case 3, I will have to make sure that the data comes to its original position if I had missed at least, I mean, even if I missed 1 bit, right? So in that case, or in these 2 cases, I will have to wait for some time. So case 2 and case 3 will also add some delay to my retrieving of data, right? So this delay in retrieving the data is actually called as latency. So we are not still talked about worst case latency. I'm just talking about latency. All right. Now let's say if my information was here, okay, and then I started reading. Now I'll talk about 3 to 4 positions. One position is this. Okay, I'm just marking it with some broader lines, right? So the one position is this, second position is this, third position is this, and fourth position is this. Okay. So and okay, let me also name these positions as A, B, C, and D. Okay. Now let's say if my data, I mean, so we are now we'll talk about the instant the actual data was when I started reading or when the lens started reading the data. Okay. So let's say if the data was here, 1, 1, 0, 0, 1, 0, 1. And at this instant, if the lens started reading data, what will happen? It will have to wait 3/4 of the circle, right? It will have to wait 3/4 of the circle. If that is the case, for case C, I will have to wait half the circle. Okay. And in case D, I'll have to wait quarter of the circle. So what will happen? The time taken by data to reach to its original position depends on where it is initially, right? Where it is initially. So if it is at B, it will take more time to reach to position 1. When it is at C, it will take somewhat less, but time to reach to position 1. And in D, it will take least time to go to position 1, right? In what case it will be most? Right? Now we need to find out what case it will be the most. Okay, so we'll consider this point A where the lens just missed the data, just missed. All right. So we can say that it is at position A, but it is not, I mean, exactly at position A. It has just missed the site of lens. In that case, what will happen? It will have to go through the entire rotation of the disk and then get retrieved by the lens, right? In that case, the delay will be maximum, right? So if I say the order of delay, the delay will be maximum at A, I mean A plus. Okay, I hope you understand what this plus is. This is not exactly at plus, but it is somewhat or very small value ahead of position A. Okay, then it will be greater than B. The delay of B will be greater than C, and the delay of C will be greater than D. This means it will have least delay when it is at position 1, 1, 4. I mean, in this case, Otherwise, least delay it will have when exactly when it was reaching, I mean, entering the lens and it started reading. In that case, there will be no delay or very less delay, right? So, I mean, that position I can call it as A minus, right? Just below the A. Okay. So this would be the delay that you are getting maximum. Okay, so what is that case? In that case, you'll have to just consider that the data has just passed the lens, so the lens is still not able to retrieve. I mean, it just missed the lens. In that case, lens will start retrieving the data only when it has taken the entire circle or the entire disk rotation and come back to position number 1 or A minus, right? That is why this question, when I say worst case latency, I will have to find out how much time does a point on the disk. Now that point on the disk refers to the starting point of data, right? So to find out worst case latency, what I have to do? The time taken by this point to take the entire rotation of the disk, right? For that, we have been given the actual speed of the disk, right? So I hope now you got the scenario what we are talking about in the question. All right, and why calculating why revolution, that is 7200 revolutions per minute, speed of disk makes sense here, why it is given. All right, why are we talking about worst case latency? Okay, and why are we talking about position A plus when we are talking about worst case latency, right? So I hope this part is clear. All right, now what remains is the calculation. Okay, so I'll just I'll keep this part, but I'll write it here. Okay. Delay A plus greater than B greater than C greater than D, and this D is actually nothing but A minus, not D, and it will be greater than A minus because A minus is this position, right? D is this. Okay, so you have to just keep this in mind. Now I'll just remove this part, try to erase it. Okay. Now, so we'll use the data given in the question and find out the time taken by this point to take one rotation of the disk, right? So since there are 720, I mean 7200, pardon me, not 720, 7200 revolutions per minute, I will say per 60 seconds, right? 7200 revolutions per 60 seconds. Okay, so if I solve this, I will get 120 revolution per second, right? If it is taking 120 revolution per second, I need to find out the time taken for one revolution, right? Time taken for one revolution in seconds. Okay, so what I have now, I have revolution per second. I need to find second for one revolution. Okay? I need to find out time per revolution. So what I need to do, simply take the reciprocal of this now, right? So if I do this, let me see, comes like, yeah, so it gives me 8.33, I mean 8.33 is recurring into 10 raised to power minus 3 seconds. Okay, so it gives me 8.33 into 10 raised to power minus 3 seconds. This 10 raised to power minus 3 second is nothing but milliseconds, right? So 8.33 millisecond is the time taken for any point to complete one entire rotation, right? So you need to understand that this A plus and A minus are separated by a very minute distance, right? That you cannot measure. Okay, that's why we are taking, I mean, considering this to be the entire circle. All right, we are not removing that tiny piece of part. If you want to really go that exact, you can subtract the arc which is equal to the diameter of this lens. Okay, so better not to consider that. All right, so what you can what you get now, the time for any point to take one revolution of the disk is 8.3 milliseconds, right? So I can consider, if my data is starting, if my data missed this lens, just missed this lens, it will take 8.33 milliseconds to come back to the original position where it is possible for the lens to detect the data. That is why we are calling it to be the latency. Now, as I said, the when it will be the worst case latency, where my data had to travel the maximum distance. What is the maximum distance in the case of disk? The entire revolution. Okay, that is why we'll take the the entire revolution for worst case latency. All right. Now there can be variations of this question. I hope this part is clear. So this is all about the question. Right. Now we'll talk about some variations. For example, let's say the variation I guess you can assume that what can be the variations. Let's say I can define the position. Right. I can say that the lens started reading when my data has already passed 1/4. If it already passed 1/4, it has to cover 3/4. Right. So that what you have to do, actually, it is the time taken for one revolution. Okay, now if my data if I give the situation that my data has already passed 1/4 of the revolution when my lens actually became active, what you need to do, you need to find the time for the data to cover 3/4 of revolution. Right. So it is nothing but linear. Right. So if it 8.3 is for complete revolution, for 3/4 of revolution, it will be 0.75. Multiply the entire time by 0.75. Okay. In case of half the disk, you can say 0.5 and 0.25 and so on. Right. So this was about the question. I hope I made the scenario clear. Any doubts here?
So we ignore a 2 and 3 case.
Okay. Ignore as in?
Like we won't consider that because partial data is in front and partial data is back.
Yeah, that's what. So what I said, when the data is partial, how will you bring this 3 bits, right? This 3 bits is gone. Okay.
No,
And in case of 3, the entire data is gone.
but it
Okay.
can revolve around, right? Like it can be one revolution plus
One
right?
revolution plus.
Plus the time, like wherever the data is, it passes through and then comes back again to one revolution, right?
No. So let's see, this is center. Okay. So if my data is here, okay, I can retrieve it nice and fine. Okay. If my data crosses this, I will not be able to retrieve this. Okay. So what I'll have to do, I'll have to wait in either case. In case 2, 3, in any case after, which is not this. In any case, which is not this, what you'll have to do, you'll have to wait for the data to go back the entire disk and come. All right. Now you have to. Now it depends where the data was. Right. If the data is here, I'll have to consider the remaining path. If the data is here, I'll have to consider the remaining path. Okay. In case of worst case, what will be the condition in worst case? The maximum time. When will be the maximum time? If my data just passed. Okay, just passed. Even if my single bit is gone, I will have to wait for the entire data to, take the revolution and come back.
Okay, thank you.
Is it what you're asking?
Yeah, okay, thank you. Actually, what I meant was like if my data is halfway through, it will take more than 8.3 milliseconds, or will it be 8.3 milliseconds itself?
It will take less than 8.3, right? Because it is halfway through. What you're saying here, position C.
No, in A only, but like my data has passed, like there are 3 bits in front and 3 bits back, right?
Okay.
So like the case 2 and 3 that you said.
Yeah,
So,
that's what. So see, if there is, even if one bit has crossed, you have to disqualify the data, remaining whatever is there.
yeah, so that is why we take the last case, the first case, right? When it's almost like at the end.
Yeah.
Okay.
Yeah, that's what. So I mean, see, for example, considering your case, 1 bit, I mean 3 bits after and 3 bit before, you can say that your data is yet to pass, even the pass, I mean complete data is yet to pass, right? But we are not really bothered about length of data, because it is not 6 bits or 7 bits long data, right? It can be 100 and 200 and more than that in kilobytes, kilobits, right? So it can be complete circle one around the other. Okay, what you need to consider only is the starting point. Where is the starting point? Okay, so if this is my lens, if this is the reader of my lens, and I need the three conditions that I need to consider is the data before, exactly at the lens, and after. Okay, if my, and this is the starting point, data follows, and we are not bothered about what is the length of data, how many bits are there. Okay, we are only bothered about the head. So if the data is just below the lens and lens is yet to I mean retrieve, no issues. Okay, because it can still start and start retrieving the data. Okay, if the lens just started where my data was crossing it, that is okay. But if my lens somehow missed the head, it will have to wait for the entire data to come back, take the entire rotation and come back, right?
Yeah, correct.
Yeah, so we are not really bothered about, I mean, 3 bits here and 3 bits there. If head is gone, it's gone. All right.
Yeah, got it. Thank you.
Okay. Any other doubt on this question? Okay, fine. So we'll move ahead. You can take the screenshot even, but I will share you the, I mean, this file. Okay. Yeah. So this is again a question, a part of practice question in week 7. All right. And generally I take the numericals of week 7 and 8 together, but 8 I have tried to skip as far as I can. All right. But you can ask down, but this is okay. All right. So what is happening here? There are two search functions. Okay. And by the term search functions is basically it is a function of time. I mean, it is a function of number of inputs. I hope if you have studied basic maths, you can say this, right? Y of x. What does this mean? There is a function called y, which is a function of x. Okay, so the value of y completely depends on value of x. Okay, so that is what we are doing here. So this is 1000. Let's say I take p1, 1000n plus 200. What does it mean? The time value that you want to calculate depends on number of what is the number of input, okay, or the size of input. Okay, the input of size n, right? So the size of input, so it depends on the size of input. Okay, so what we can say, the time is the function of size of input. That's why we are calling it search function. All right, so here if you see the time has direct proportion with n, right? When the time has direct proportion with n, I mean, now what is direct proportion? That is, you don't see any exponents of n. There is no power of n, or what the power of n is 1. Okay, so in that case we'll say that the time is directly proportional to n, and in that case this is called as linear function. Okay, why linear? Because this function satisfies the equation of straight line. Okay, okay, so those who don't know the equation of straight line, it is y equals to mx plus c. Okay, so what does it mean? The y will change with respect to x, okay, and with this slope. Okay, so we'll not go into details of lines, but just need to understand that y and x are linearly dependent. Okay, and in that case they must lie on a straight line. I mean, value of one giving the value of other, that is value of x giving value of y, should together form coordinates or points in on a straight line. Okay, this is the idea. All right, similarly if I see the t2 function, equals to n cube plus 5. N cube plus 5. All right. So what is happening here? In n cube plus 5, as I said, the power of n specifies what type of function it is. Okay. Here, if I see the power of n is 3, I will say that my time is directly proportional to n cube. Okay. If it is directly proportional to n cube, I cannot call it as linear. I can call it as cubic. Okay. This is a cubic function. All right. Now only this part and this part are called as polynomials. Okay. So that's why you may have come across a term called as polynomial function. So both are polynomial, no issues with that, because they are directly proportional to some, n or powers of n. They are proportional to n or powers of n. Okay, and other than that, there is nothing. Okay, so they are polynomial. Now polynomials also has types. Okay, so linear is also a polynomial, quadratic is also a polynomial, and the one we are seeing here, cubic, it is also a polynomial. Okay, so there are two such functions, and the time that they take to give answer, okay, the time that they take to give answer depends on the size of input. Okay, so if I give one input on t1, I'll get some time. I'll give the same input to t2, I'll get some time, and then I'll have to compare which one gives better, less time. Okay, a better search function would be the one that takes the less time, definitely. Right, now what is this? Which function is better if you're sure that the input size n is always less than 10? Okay, let's not worry about this. This is very question specific point. All right, so you are being said that you have to consider that the size of input will always be less than 10. Okay, now how does that affect? We will see later. Okay, but currently we will need to understand, okay, what takes the time, or which one of them takes the less time. Okay, so I'll just remove this because I'll be just wanted to write something. Okay, now, so there is a shorter way of doing this question and a proper way of doing this question. Okay. Okay, so the shorter way would be to just put the value of n. Okay, see, always what we are saying, the input size is always less than 10. It is specifying that it is always less than 10. Still, I would say that you put the value n equals to 10 in both the function. Put n equals to 10 in both the function. So what will get? T1 of 10, right? So I'm putting the value of n. So it would be 1000 into 10 plus 200. So it will be 1200, 10200, and the value would be nanoseconds. Okay, it is given nanoseconds. And similarly, if you do for t2, that is 10, what you will get? 10 cube plus 5, right? So the answer would be 1005 nanoseconds. So here we can compare that the time taken by function 1 is greater than, it's quite greater than, right? It is order of, 10 times more. So it is quite greater than the time taken by t2 function. So which function is better? Definitely t2. Okay, this is one way of doing it. Okay. So what we have done, we have just taken, made use of the last statement that was given and took the number. Although this statement doesn't say anywhere that you have to put 10, right? Because had it been something like this, which of the following function will perform better for the input size 10, right? For the input size 10, you definitely put 10. No issues with that, and this would be the only solution to that. Okay, but what are we saying? The function is better if you're sure that the input size n is always less than 10. Okay, so putting 10 will directly not give you the answer. Okay, here in this case, it is working because it is the, I mean, the actual answer is T2, but this will not help you in every other question. Okay, I'll just show you why. Okay, so for that, let us take a fresh page. Okay, so you can see the other questions also. I have two more questions. So what will happen? I'll draw some variations of functions T1 and T2. Okay, so this is x-axis. Sorry, this is y-axis, and the one I'm drawing is x-axis. All right, and as I said, the time functions or the search functions are functions of time. Sorry, functions of size of input. Right. So on the x-axis we'll put n, and on the y-axis we'll put time. Okay, I hope this is clear, right? So the function, I mean, in any function or in any equation, a dependent variable would come on the y-axis and an independent variable would come in the x-axis. Here, time is dependent on size of input, but not the converse is not the true, right? Not the otherwise, right? So here, size of input is not dependent on time. So dependent quantity coming on y and independent on x. All right. So let's say I have a point 10. Okay. And if you see, okay, see, I'll just move this slide there, right? So that this is a slide. Right? I'll move it here so that we can see. So if you see, both these functions, I mean, both these search functions are nothing but function. And if you're talking about any mathematical function, it can be plotted, right? So as I said, it follows or it satisfies the condition of a straight line. It is easily plottable and can be seen on the graph, right? And the other one is cubic, so that can also be plotted. But just for instance, just for the example, consider both are linear. Both are linear. Okay. So I have this one point. Okay, this is point 10. This is one function. Note that I'm drawing straight line, although it doesn't look straight, but it is a straight line in the other function. Okay, this is the point 10. Okay, and let me draw the same thing once again. This is again n. This is t. Okay, and this is 10. And I'll draw the dotted lines later. Okay, this is again one function, and this is again the other one. All right. So in this case, let's say this is T1 and this is T2. Although T2 is not linear, I'm asking you to assume T2 is linear. And in this case, this is T2 and this is T1. All right. What we have done, yeah. So what we have done, let me see that. What we have done, we have found out at point 10 what is happening. Okay. So just pardon me for a second. This is not 10. This can be any other number. These are the numbers when these functions are intersecting. Okay, these are the functions where these points are intersecting. Okay, so let me go back to take the pen. All right, if my 10 comes here, if this is the 10, okay, what is happening on 10? I mean, when n equals to 10, my t2 is less than t1, right? So if I plot it on the y-axis, I mean, take the projection of these 2 points on y-axis, I can see that t2 is less than t1, which is the case we are thinking we are handling, right? This is the case, okay, which came here, right? T2 at that at n equals to 10 we got 1005, and T1 at n equals to 10 we got 10200. So we are assuming that this is the case. We are assuming, okay. What if the case is this? Not this same thing. Just let me remove that for removing the confusion. What if the case is this 10? Okay, that is here. So in this case, what will happen? T1 is less than T2, right? T1 is less than T2. All right. And now this was 10, right? This was 10. Now let us consider what is happening at this point where they are actually meeting, right? Let's say this point is 8 because I've drawn it, I've drawn 10 after, after that point. So consider this point to be point 8. Okay. So what is happening at point 8, both T2, T1 is equals to T2. Okay. But this is the story of only point 8, right? When n is equals to 8. This is not the entire story, right? So what is happening after, after 8, my T2 is better because it is taking less time. And before 8, my T1 is better because it is taking less time, right? Similarly, if I go here, again, 8, same thing, right? After 8, in this case, when I've interchanged, after 8, my T1 is taking less time. And before 8, my T2 is taking less time, right? Now, if I go back to the question and read this statement, which function is better if you are sure that the input size n is always less than 10? We are talking about input size n that is less than 10. We know the story, what is happening at 10. What is happening in less than 10, you cannot find out, right? But by simply putting in 10, can you really comment on what is happening before 10? The same thing is happening in our case for case number, where n is 8, right? So from this we can infer that. I hope, before I go ahead, is this clear what I'm trying to say here? Any doubts? Any confusion I'm creating over?
No, sir, no any confusion.
Okay, fine. Yeah, so basically what I'm trying to say, I'm just trying to say that at one instant, you cannot comment on the exact range or entirely on the function, how it behaves, right? Because you know the story of only one instant. Okay, so here I found that for n equals to 10, my T2 is better. Okay, and then for this question, I'll comment that, okay, for which function is better if you're sure that input size n is always less than 10. Okay, now if I see this, what is happening? For only 8 to 10, from 8 till ahead, after 8, I can say that T2 is better. But before 8, what is happening? T1 is better, right? So for the input size less than 10, I cannot simply comment what is happening actually, right? So it is very important to understand the range where one function is performing better than the other. All right. So a better scenario would be, a better understanding of this graph would be, for n greater than 8, for n greater than 8, T2 is better than T1. All right. And for n less than 8, T1 is better than T2. All right. So now I'm saying T1 is better than T2, but I'm also defining at what range. I'm saying T2 is better than T1, but I'm also defining where exactly. Okay. And this is really important. Okay. Now let's say, now I'll try to explain the actual condition. Actual condition. Okay. Now I can say that for this condition, let's say when I say, can I say that for this condition, or let's say one condition, I'll just take a statement. What is the statement? I'm saying that T1 is better than T2 if I'm making sure the number of, or the input size is always less than 8, right? I've just made this mathematical statement into a statement. I've just told this mathematical statement to a statement, right? So what I'm saying this in words. T1 is better than T2, but it is subjective. Depends on what? Actual range. So here I've given the range. Okay. For n less than a, T1 is better than T2. Okay. Which is pretty much similar to this. Right? Which function is better if you are sure that the input size n is always less than 10. Right? So what we are doing, we're trying to find out a range where one performs better than the other and then comment. That would be the better approach of solving these type of questions. All right. So what I'll do, what I've done here, how was I able to find which one performs better than the other? Because of this point, their intersection, right? These intersections give me a better idea to say, okay, which performs better than the other. Okay, and then I can set the range. For example, if I have something like this, now I won't name anything, but I'll write something like this. This is one function and this is the other function. Okay, what is happening? For this range, my linear one is better. For this range, my curved one is better. And from this, for this range again, my linear one is better. And for this range, here onwards, just extrapolating, all right, onwards, the curved one is better. How can I define these ranges? Because I know the critical points. These are the points where they intersect. Okay, because when two things intersect, they tend to change the course. Right. So this is what we are trying to understand. All right. So if I have the idea of these critical points, or what we call as the roots of two equation, these are called as roots of two equation, right? So if we know the critical points, we can easily say in what range one function is better than the other, which is a more correct answer, a better answer than simply saying that T1 is better than T2 or T2 is better than T2. Right. So what we'll try to do, we'll try to find out. I'll take a new slide. I will try to find out the roots of this equation. All right. So roots of this equation, or how to find the roots of this equation, we'll simply say, okay, what is happening here? These are the points where these both functions are intersecting. Intersecting meaning they give same value. Both of them give same value of time. Both of them give same value of time. That is, for what n, basically what I'm trying to do, I'm trying to find out for what n or n's T1 is equals to T2. T1 is equals to T2. I'm trying to find all those value of n's where T1 is equals to T2. Okay, so I'll just take the equation that we have. All right. The one equation was this, let's say T1 n. This equation was 1000 n plus 200, and the other equation was n cube plus 5. All right, and what we want to do, we need to equate these two. All right, so what we'll do, 1000 n plus 200 is equals to n cube plus 5. All right, so this becomes a quadratic equation. We just have to, let me rearrange this, minus 1000 n, okay, minus 195 equals to 0. All right, and there is a square term missing, so we'll just try to find out the value of this the value of n's for which this equation becomes 0. I have a calculator, I'll get the answer. Just a minute. Okay, so one value of n is 31.71, let's say 72, 7198. Okay, the other value is minus 31.52, and the another value is minus 0.5. 195. Should I write it 2? Yes, minus 0.2. Okay, so these are the three values where these curves intersect. All right, and it is pretty much evident that we'll have three values because this is the, you know, highest power. So this is called as degree of equation, degree of polynomial, right? So the degree of polynomial determines how many roots are going to be there for the polynomial. Okay, so this is so these are the three values. This means what? If I draw the curve, if I try to draw these both curves, I will see that they are intersecting at three different points. Okay, so what are those three different points? 31.72, minus 31.52, and minus 0.2. All right, so I'll try to just draw it, not the exact figure, not to the scale. Okay, and so it will be something like this. Sorry. Okay, this is this function I've drawn, n cube plus 5. Why I have taken this plus I mean why I have left this space? Because of this 5. Okay, so n cube it shifts up. All right, and the other one is 1000 n plus 200. So again this is 1000 n plus 200, so it will shift something like this up. Now if you see, this is 5 and the other one is 200, right? So it will give very high. So just let me change the curve a bit, something like this. Yeah, because I want to show the 200 also, right? And the other one would be something like this, my linear. Okay, okay, so these are the three intersecting points. This is 1, this is 2, and the other one is 3 somewhere here. Okay, these are the points that I know. Okay, what are these points? Minus 31.52. Okay, this is minus 0.2. Okay, and this point is 31.72. All right, now I have a better range, right? Now I have a range, I have a very good range. Now you need to see that n cannot be less than 0, right? It cannot be less than 0. Number of, or the size of input cannot be negative. Okay, so we will consider only this part, the positive one. All right, and this point, if I try to project it on x-axis or the n-axis, what this would be? 31.72. So n, as n cannot be less than 0, this will be n equals to 0. So what I can see, my T2 is better than T1 for this range, right? Okay, now if I have to answer, if I make sure that n is always less than 10, I will never go more than 31.72. If I never go more than 31.72, T2 always remains better than T1. All right, if T2 always, I mean in the range 0 to n, or like this, T2 always remains better than T1. This is a better answer. I gave the same answer which I gave, 10-15 minutes back, but this is a better answer because now I am also providing the range. Now if somebody cannot come with the doubt, sir, I check with 15, still T2 is better than T1, right? So why I'm saying this? Because the question says, okay, if I'm making sure if the input size is always less than 10, what about if the input size is greater than 10? Okay, for the input size greater than 10, will it be the case that T1 will be better than T2? No, it can be, but only after 31.72. So if somebody comes and asks me, okay, what will happen with 15? You should not get confused that, okay, why if before 10 it is giving me T2 better than T1, after 10 it should give me T1 better than T2. That is not the case. That is not what we are trying to say with this question. Okay. So 31.72 makes the difference, not 10. Okay, so you cannot have this confusion that, okay, for 15 also T2 is better than T1. Then what does 10 mean? Okay, 10 means just the size of input we are specifying. Okay, even if I said, had this question been something like this, which function is better if you're sure that the input size is always less than 30? In that case also, the answer would have been T, right? So I hope now this is a more analytical way of looking at this question, right? Which gives me the exact range, and I will be in a better position to answer which one is better when. Okay, is this clear? Any doubt here in this question? I'm sorry for the background noise. I'll just move for a minute. Yes, so if there is any doubt, you can simply unmute or put it in chat, and I'll try to answer.
No doubts.
All right, so I'll consider that that question was clear. You'll have this slide altogether, right? So I'll provide this slide. All right, the next, yeah, somebody speaking. All right, okay. Okay, one similar question, but here only the way of looking at it is different. The way of looking at it is, I'll just explain. All right, so I hope you have read this question. Probably in the quiz. So this question was a part of quiz in the previous terms, right? Software packages A and B of complexity O of n log n and O of n respectively. That is A O of n log n and B of O of n. All right. Spend exactly T1. So see, these are the complexities only, but the actual function that defines these software packages are this and this. All right. Milliseconds to process the data. During a test, the average time of processing 10 raised to power 4 data items with package A and B is 200 milliseconds and 600 milliseconds. Okay. Work out the exact conditions when one package actually outperforms the other. Now, this is the actual question, or this is the question that will, I mean, okay, let me take those three questions back to where they were. Right. So this is the question. This is page 1 of its solution. This is page 2 of its solution. All right. So now let's see. If I go back to this question, all right, and if I ask you, work out the condition for which T2 is better than T1. Okay, you cannot find out unless you know this thing, right? What you have done here. Okay, this is one way, and this can be solved with other way when other type of information is given. All right, so other type of information is that is what we are seeing in this question. All right, so what they have done is, so there is T1, so I can write TA, all right, TA equals to C n log, so this is not log 2n, this is log to the base 2 of n. All right, this is 2 base. All right, and the other function that is TB is T n. All right. Now see, in this function, you see a product of n log n. That is the reason we are calling TA has a complexity of O n log n. All right. This base doesn't matter. It can be 2, 10, anything. All right. And this is not Tn, it is Cn. All right. If Cn, I can say is Tb directly proportional to n. If this is the case, I can call this function as linear. Okay. All linear functions have the complexity O of n. Okay, which is given. Additional information, don't have to worry about it. Okay, so these are the, you can call this function also as linear. Same thing, same thing that we have done in the last question. Only that there the time was in measured in nanoseconds. Here it is in milliseconds. This is one difference, and we have two different functions. In the previous case, both were polynomial. Only the degree was different. Here, one is logarithmic, all right, and the other is linear. Okay, it doesn't matter because ultimately it comes down to calculation. All right. So what we need to find out? Yeah. So we need to find out some actual function, right? Right. So here, let's say in the initial function. Now let me compare with the previous one. What was T1 there? T1 was 1000 n plus 200, right? And T2 was n cube plus 5. Let's say if I say T1 is, so these are the complete functions, right? All numerical values. There is only one variable or one unknown, that is n. All right. Now, if you see this, if I write 1000 n instead of 200, if I write a, okay, and for T2, I'll write n cube plus b. Would it have been possible to find out these three values if no additional information was given? No, right? We had this 200, this 5. That's why there was only one unknown and one cubic equation. Here, we are having three unknowns, n, a, and b, right? So we might need some extra conditions to figure out what are these values of a, right? Similarly, if we see these functions, this function is not a complete function because I have an unknown called as c, and n is already there. Okay, so to figure out what c is, I have additional information given. Similarly here in TB, there is c unknown. To figure out what c is, the additional information is given. Okay, so what is the information given? Let us simply put it in the equation and say. So what we are trying to do, we are figuring out 10, processing 10 raised to power 4 items, and the time for that is 200 milliseconds. Okay, so I can simply write 0.2. Okay, I'm writing in seconds. Seconds as in, for calculation, you will have to always put the SI units, right? Seconds. Although you are getting, the time, these are the equations. That's why the unit is in milliseconds, no issues. But for calculation, you'll always have to put the actual values in seconds. Okay, so 0.2. Okay, C is something that I don't know. All right, and n is something for that particular case. When is I'm getting 200 millisecond. When is that I'm getting 200 millisecond? When n is 10 to the power 4. All right. All right, and here also I can say log to the base 2 a. You can consider this 2 as 10. Okay, because in that case the calculation becomes a lot easier. Okay, so I'll just remove this. I'll put 10. Okay, so log base 10 and n is 10 to the power 4. Okay, answer will come with the 10 raised to power 2 also. I'm just trying to make the calculations easy. Okay, so here I'll get C's value because that is the only unknown remaining, right? So this is 0.2 equals C into 4, 10 raised to power 4. I hope you know this, right? Log to the base 10 of 10 raised to power 4 is nothing but 4 that I've written here. Okay, so from this we can find the value of C, which is, in a minute. So you can write it as 5 into 10 raised to power minus 6. Okay, let me cross check. Yeah, so it is 5 into 10 raised to power 6. So this is C for TA, I mean this function. Okay, so I'll write just CA here. Okay, similarly we'll do for this. Okay, so it is 600 milliseconds, right? So 0.6 is equals to C into 10 raised to power 4 directly. Okay, so this gives me C equals to 6 into 10 raised to power minus 5. Is it right? Just let me check. Yeah, 6 into 10 raised to power minus 5. All right, now that we, and this is CB. All right, now that we have the values of C of both the functions, we actually have the entire function now, right? We actually have the entire function. So I'll remove this, right? This is just to explain, right? This is not required. This is the part of other question. Sorry for being slow in routing. Yeah. So what is my first function? That is TA. I can say that it is 5 into 10 raised to power minus 6. Just substituting the value of C, right? N log N. Okay. Please note this 2 is 10. Okay, and TB is 6 into 10 raised to power minus 5 N. Okay, now what we need to do, we need to find out at what, okay, so we need to find out or recommend the best function that will give me lesser time for 10 raised to power 10 items. So I'll simply find time for both. Right, now see, here I don't need to find range. Why I don't need to find range? Because I'm specifying that my n is equals to 10 raised to power 10. Okay, I'm not specifying for, okay, what will be the better function if my size of input is less than 10 raised to power 10, or I'm making sure that the size of input is less than 10 to the 10 raised to power 10. I'm not talking about anything about range. I'm exactly specifying at that instant where n is equals to 10 to the power 10, what is the case. So in that case, you have to worry about that single point, not the range. Okay, so I'll simply put in the value. Okay, so it will be 5 into 10 raised to power minus 6 into n. So it is 10 raised to power 10, and this will give me 10, right? I hope this is clear. Log base 10 and 10 raised to power 10. So 10 drops. So it is 10. So what do I get? I'll have to calculate this, right? So it is 5 into 10 raised to power 5 into 10 raised to power 5, right? And the answer is in milliseconds. Okay, so I can say that it is 500 seconds. Okay, 500 seconds, because see, if the unit is milliseconds, right? So I'll also say 10 raised to power minus 3 in second, so it becomes 500 seconds. The same thing I'll do with this. So it is 6 into 10 raised to power minus 5 into 10 raised to power 10. So this comes out to be 6 into 10 raised to power 5, which is nothing but 600 seconds. Okay, 600 seconds. So which one is better? TA, right? For that particular point. So you don't have to find out the range. Okay. Is any doubt here? Is this clear? Okay, so we need to understand why any information is given in the question. I hope this is clear, right? So, I mean, a lot of understanding in this has been explained in the previous question. So I hope this is clear. Any doubts, or we'll proceed with the next question? Yeah, so you, I mean, you can expect similar questions in quiz and term.
So one thing, that log you said, right? So won't that be specific question? Like, how do we know it's log 2n or if it's log based to n?
Yeah, it will be specific.
And one more thing, this is up to n is equal to 10 raised to power 10, right? It is not equal to 10 raised to power 10.
Yeah. No. See, here n equals to 10 raised to power 10. I'm specifying, right?
Yeah.
Okay, what you're saying is okay. What you're saying is work out the exact condition when one package actually outperforms the other and recommend the best. Okay, yeah. So this is one step ahead, right? What is the step? The one that we have done in the previous question. So what we have done exactly? We have found out that for 10 to the power 10, which one performs better. Now we will give the exact condition where one outperforms the other. I mean, what exactly is the point where you will see that okay, there is fluctuation or the course of values are changing, right? So what is the way of doing that? I'll just get back to the new page. I'll just write both the functions and equate them, right? Just to find out the critical point. Okay, so it will be TA equals to TB. Okay, just correct me if I forget the function. So it was 5 into 10 raised to power minus 6 into n into log, sorry, 10 n equals to 6 into 10 raised to power minus 5 n. Just let me check the value of c and the other. So it is 5 into 10 raised to power minus 6 and 6 into 10 raised to power minus 5. All right. Yeah. So what we'll do, we'll find out this value. This n gets cancelled with this n. Okay. So we get log the base 10 n equals to 1.2, is it? I've just divided this by this 1.2 or 12, right? 6 into 10 raised to power 5 divide by 5 into 10 raised to power minus 6 is 12. Okay, and then we'll find out. We will find out what this value of n is. Yeah. So what is the value of n? N equals to 10 raised to power 12, right? Right. N is 10 raised to power 12. So what is happening? What I did, let us try to draw this. Okay, a logarithmic function will be something like this. Sorry. Something like this. Logarithmic multiplied by n. So it is n log n, right? And a linear function will be something like this. Okay. So we need to, okay. So we know that at 10 raised to power 10, these values intersect. Okay. Both give the same answer. Okay. And we know that for 10 raised to power 10, TA is better. TA is better for 10 raised to power 10. Okay. So we will draw it in that sense. Okay. So there is a point 10 raised to power 12. This is where these both are same. And then there is again a point 10 raised to power 10 when TA, that is the logarithmic function, is better than the linear function. So it will be something like, sorry, I don't want to be, I mean, I cannot be exact with the curves. It will be something like this. All right. And my linear function will be something like this. Okay. So this is where both are same. And this is where this is, sorry, TA. Okay. And this is what is TB, the linear one. Okay, so I can define now. Again, I will not go into the positives, sorry, in the negatives. All right, and I don't know what these points are. Okay, I guess these will be zero. Both will be zero because both are linear. Okay, so both will be zero. Okay, so for the range, 0 to 1, hello. Sorry, I got disconnected, but I want to know where till what instant you saw. Hello, am I audible?
Yeah, you're right.
Okay, so I
In
mean,
the
let me share
graph
my screen back.
logarithm.
Just give me a minute. Where is that collab? Yeah, so just wanted to know till what point I was there. Is this clear, by the way? I mean, this is what I was trying to say, that if we try to draw somewhere the logarithmic and the linear function, this is the point where I will see that, okay, 10 raised to power 12 is the point where both are equal. All right. And I know that in 10 raised to power 10, TA is better. So it will be drawn something below, right? And then the question asks, work out the conditions where we're talking about up to 10 raised to power 10. So up to means 10 raised to power 10 and below till 0, right? So in all that range, TA will be better. I mean, the one giving that gave the lesser answer. Okay, now what is happening? I'm able to find out the exact point and able to deduce TA was better. Why? Because my range is not affecting me that much. All right. What if I had asked work out the exact conditions when T2 outperforms T1. Okay, T2 outperforms T1. Right. Finding T n for n equals to 10 raised to power 10, I'll know that okay, T is giving me lesser answer. That is okay. But if I ask for, let's say, a condition 10 raised to power 14, okay, in that case, what we will there is a chance that we give a wrong answer, right? So in that case, range is very important. And at what case, I mean, in what condition we are exactly asking. So that is important, right? So if you have the knowledge of range, you will be able to answer at any point that is asked. Okay. So here, that is the same thing that we have done. We have found out the range. Now, this is the range for which TA is better than T2. Now, if 10 raised to power 10 comes in this range, yeah, TA is better than T2. Okay, you don't even have to find these answers, uh, these two answers, if you know the graph, right? But that is okay. I mean, you perform for exact condition, and we will not try to give you very complicated graphs so that you are not able to answer, but you will always be able to find the range. We will not give you this question also. Why? Because it has a quadratic, and finding roots of quadratic without a very good calculator is not possible. So we'll not give you questions like this. It can be a simple quadratic, not the quadratic, sorry, cubic. A simple quadratic can be given where you can figure out the factors. Okay, so we'll not give you like this is for understanding. All right, any doubt here? Okay, so the two things to take from this question, one is the which one is better at 10 raised to power 10, and the other is which one outperforms the other and at what point, which is 10 raised to power 12, as we saw. Okay, so these are the two things. All right, so this is the next question. Before we go to this, just wanted to know if this is clear. Okay, I hope it is. You can refer to this recording again. Yeah, somebody speaking.
No, sir, clear.
Okay, okay. All right. So how many of you got this question correct? This is a question from practice and graded, I guess. Graded week 7. How many of you understood this question? Okay, fine. So see what we are trying to do here. We are writing an algorithm to sort n numbers. Okay, this is what we are trying to do. I mean, there are n numbers in a list. Let's say there is a collection or there is an array as given here. Okay, and those numbers are currently not sorted. Okay, now what we are trying to do is we are trying to sort the numbers with the algorithm that is given here. So we are using these steps to sort the numbers, and then we have to find out what will be the complexity of that algorithm. Okay, there can be multiple ways of sorting numbers. All right, some that I myself don't know, but this is something that is given, right? This is the given algorithm that we have followed. Okay, so I'll just try to explain what the algorithm is. Okay, let's say I have an array. Okay, and there are numbers 2, 7, 5, 3, 8, 6, 1. All right, this is an array unsorted. Okay, now I want to sort this array. Okay, so what we are doing, search through the list of numbers to find the lowest number. All right, this is the lowest number we have to find. All right, so the worst case to get the lowest number is you have to compare, right? You compare this with this with this with this, so many comparison, and then you will find out, okay, finally you come to this is the number 1 in this array. 1 is the lowest number. Okay, the complexity to find lowest number by performing those many comparisons as there are numbers is called n. Okay, so the complexity to find the lowest number in any list, see, we are not sorting, we are finding out the lowest number. Okay, so the complexity to find out the lowest number by comparing all the numbers is n. Okay, n. Now once this is done, what I'm doing here, I'm shifting it behind. So what is the move a I minus 1? Okay, so let me also write the index. This is 1, sorry, 0, 1, 2, 3, 4, 5, and 6. All right, so what is the value of I? 6, right? Search through the list of numbers to find the lowest number. Say it is, I mean, say its position is I. Okay, so the position of that number is I. So this 1, which is the lowest number, is at the 6th index. All right, now what I have to do, move ai minus 1. What is ai minus 1? 1. Okay, ai minus 1, right? So a of I minus 1, a means array. Okay, so this a is the array. All right, what we have to do, we have to keep moving this number. See, this ai minus 1 has to be shifted to ai. Okay, so what will happen, first I'll remove this. Yeah, somebody speaking. Okay, I'll remove this. So what will happen, now my array becomes like this: 2, 7, 5, 3, 8, 6, and space, nothing in position I. All right, because I have removed it. Okay, so this is 1, I have placed it here outside the array and I have removed this. Okay, so ai minus 1, what is I? 6. ai minus 1, that is a of 5. All right, what is a of 5? 6, right? You can see this is a of 5. What we are doing, a of 5 is moving to a of I. I mean, a of I minus 1 is moved to a of I. That is, a of 5 will move to a of 6. What is a of 6? This blank space. All right, so this shifts here. Okay, I'll try to erase this part. So when 6 is shifted to its its next position, its position will become vacant. Right. So this is 6. And if you see ai minus 2 to ai minus 1, this means a4 will shift to a5. That is 8 will shift to blank. All right. So this 8 shifts here. Now, if you notice the pattern, what is happening with every number shifting one place ahead, its place is becoming vacant, and that place is taken by the previous number. In short, everything is shifted one place ahead. Okay, everything is shifted one place ahead. So finally, my A array will become a blank space, then 2, 7, 5, 3, 8, 6. All right. Right. So this is done after finding out the first lowest number. Right. This is done after finding out the first lowest number. All right. And then what is the third one? Place the original AI in position 0. Right. So this one AI, right? So A6, original A6 was 1, which was the lowest number. That was pushed to 0, position 0. Right. Now, with 1 coming at position 0, I can say that my lowest number in this list is at the very first position. Right. This is how sorting works, right? I want to sort, I want the lowest number to come at the 0th index. Okay, this is done. Now what is happening? Repeat the above steps, but now starting from position 1 to n minus 1. What is 1? This is position 1. Okay, now if 1 is filled in index 0, I don't have to move it because my lowest number is already at the lowest point. All right. Now if I do the same thing with this list, I will end up 2 coming at the same point. Okay, if I do it this with the same list, I will end up 3 coming here. Okay, so finally my array becomes sorted. Okay, with all smaller numbers keep on coming. Every time you have to note that once the number is shifted to position 0 of that array. So this is my original array. Second time my array will be this. Third time my array will be this. Fourth time my array will be this. So array keeps on reducing, right? Why? Because starting from position 1 to n minus, then 2 to n minus 1, except. Okay, so this is 1 to n, 0 to n minus 1, to 1 to n minus 1, 2 to n minus 1. This is what I'm doing. Okay, this is how my sorting is taking place. All right. So what is happening when I was so when I was shifting, I was doing it with n numbers. Okay, comparison with n numbers. When one number gets reduced, I will do the comparison with n minus 1 numbers. All right. Okay. Then again, I'll do it with the comparison with n minus 2 numbers and so on. All right. And then once my number is found out, I will do the shifting, right? That shifting will go on with the remaining, I mean, all the numbers in the list. Okay, I found out the lowest number. Okay, for that, I will take n steps. Okay, and shifting that number to the lowest point, that will again take n steps, right? So initially, I'll take n steps to find out the lowest number. Okay, for that array. And then I will go to n steps again to get to the, I mean, to do that for the entire array, right? First, I'll do it for n, then I'll do that for n minus 1, then I'll do that for n minus 2, then I'll do that for n minus 3, right? This is how I'll keep on doing it, right? How many terms will be these? This will be n terms, right? So I'm doing n calculation. So yeah, so one point to note here. See, if I'm saying n, it is linear. Okay. If I'm saying n minus 1, n plus 1, or n minus k, n plus k, where k is constant, n is variable, right? So when k is constant, all these are linear. Why? Because there is nothing attached with n. Okay, multiply it with n, I mean, the power of n is not there, right? In that case, all these cases, all these 4 cases I've defined are all linear. Okay, so if I say n square is quadratic, 2n square, n square plus 1, n square plus 3, 5n square, these are all quadratic. All are quadratic. Why? Or what depends? I mean, what is the thing that I need to note, what is the power? What is the highest power? It is 2. This means it is a quadratic, right? But this has to be constant, right? If I am multiplying with 2n square, 2 has to be constant. 5n square, 5 has to be constant. Or n square plus 1, 1 has to be constant, right? So all these are quadratic. Now what is happening? So if this is the case, if you understood this, you will see that this n minus 1 is also n minus 2 is also n minus 3 is also n. So what I'm doing? I'm doing n operations n times, right? For every time my list is getting reduced, right? So n times I'm doing that because I will have to do it till I get the entire sorted list, right? Starting from 0th index to n minus 1 index, or n, I mean first number to nth number, right? So n calculations are being done n times. That is the reason its complexity is n into n. Okay, now what is n into n? N square. Therefore, we call its complexity to be quadratic. Okay, this is the running complexity. Any doubt here? Any point that you missed? Okay, so what I was saying here is, let's say if I talk about n, which means linear. Okay, so 2n plus 1, n plus 1, n minus 3, 5n plus 65, n by 2 plus 5, all are these all are linear, because you see there is no power of n. The power of n is 1. So when I say quadratic, I would say n square. So it can be 2n square plus 1, n square plus n plus 1. Why? Because degree is n, right? So degree is 2. So it will be still remain quadratic. What governs the graph is the quadratic part, not the linear part. Okay. N square plus 5, 5n square plus 10, everything, all these remains quadratic. Same with cubic, same with biquadratic. Okay, and it goes on. All these are polynomial, but I need, you need to make sure that this is linear polynomial, this is quadratic polynomial, this is cubic, and this is biquadratic. Okay, so coming back here, I'm doing n minus 1, n minus 2. I mean, this means I'm doing n again n again n. How many times? N times. So n comparisons done n times. That's why this complexity becomes n square. All right, so this is the question. Any issues here? I hope you understand the algorithm, right? What is happening? So you can try doing it by yourself to understand, okay, what exactly is happening, what index I'm talking about, where are we shifting. Is this clear?
So this question had an option of exponential as well. So do you have an example for that?
Okay, so yeah, exponential, yeah, it can be something like this. Exponential functions can be something like this. Let's say t of n is equals to 3e to the power n. This is an exponential function. Exponential functions are easily recognizable because they will not work without t.
So how will we figure that out from like the algorithm steps?
Yeah, so from algorithm steps, I mean, see this, if you go through this, you will figure out that n things are happening n times. So you will never come to exponential and logarithm. Okay, generally when an algorithm is given, and if I want to involve the component of exponential, I will say that the search through list is done with exponential complexity. Okay, if the exponential complexity is already used, I just need to find this n. So the final complexity would become n e to the power n. Okay, it will be given.
Sir,
if it is not given,
a constant raised to n also will be exponential, right?
a constant raised to n, yeah, this is exponential. because E is again a constant.
Okay.
2.71, 2.71 and recurring. It is a constant. Yeah, so you do not get confused between two things, right? So there is one thing called as, or one thing read as k to the power n, another thing read as n to the power k. Okay, so this is exponential, this is polynomial, right? We just saw, right, n square. So it is n raised to some constant. N raised to some constant is polynomial. Variable in the power will definitely make it logarithmic, sorry, exponential. All right.
Okay, sir.
Constant
Okay.
in the power, it will always be polynomial. Okay. Any other issues? Any other doubt? Yeah. So I mean, the week 8, the deadline is yet to pass. One thing. Second thing, the only problem, I mean, the only numericals or the problem that you may have come across in week 8 has already been taken care of, I guess. Right. So I guess that wouldn't be an issue. You'll be able to solve. Okay. Any other doubt? I mean, any other doubt regarding these questions? Or if you have any other question to ask, you can ask. Okay, so I assume there is no doubt. I'll give you this. Okay, one thing in the chat. Solution of week 8 practice assignment question 1. Okay, so yeah, let's see. But I guess that question is covered, right? That's what I'm saying. In week 8, you will have only one type of numerical that is easily covered, right? So yeah, who's this? Let me just take a name. Yeah, Pritham, what you can do is you can refer to the activity practice session of week 8, right? So we are in week 9 now. You can refer to that session and you will get a very clear idea about that question. Okay. And there is also a theoretical part of this question that is covered in discourse, right? A theoretical solution to this question. Okay, so you can also refer to discourse or that particular session. If there is any specific doubt, you have watched that session and you're still not clear, then you can ask. Okay, so I'll share this Jamboard. I'll download this and share this to you. But you can also take screenshot if you want. But I guess sharing will make more sense. Okay, so this will be shared. All right, so just a brief information about the next session. So Saturday is solve with instructor session, right? For week 9. So we will discuss about the security part of web application. Mostly we will go through, go into details of Flask login, an extension of Flask to understand the security, right? So you wouldn't want any other user to just log in into an application without any proper credentials, right? So to take care of that, we will take Flask login as a part of security solve with instructor session on Saturday. Okay, any other general doubt?
So regarding the project, will there be a live session that explains how to proceed, or do we need to figure it out?
Yeah, you can, I mean, see, regarding project, now that the project statement is open, you can ask your doubts in normal live sessions also, but we are also planning to have a separate session for project to actually explain you the question statement.
Okay, okay, thank you. And when is it planned? Like,
All right, so it will be somewhere after your quiz too. Okay, so we have, I mean, we are a bit packed for the next week also, because we'll also have to take a revision session for quiz 2, right? So we want to do that first. After that, we will be able to take a session on that, right?
Okay. Thank you.
Yeah, so you can expect it after on in any of the live sessions after quiz 2. Okay, so I'll simply stop sharing for now. Yeah, so if there are no issues, or if there are any issues, just you can ask me now. If there are no issues, we can wind up, because this is all what I wanted to say in this session. Just wanted to cover some aspects of numerical. Okay, so if there is nothing else to discuss, we can wind up, officially wind up the session.
Thank you,
Sir,
sir.
will you please look into my mail on I have sent?
Okay, all right. Did you mail me?
Yes, sir. Yes, sir.
When was it done? Now?
No, sir. Some 3 to 4 days ago. Actually, I was late in replying.
Okay, so did I reply to that?
No, sir, not yet.
Oh, really? I mean, okay, not even a single reply.
Yes, sir. You have replied, but I have sent the zip file to you.
Okay, is it a follow-up?
The
Okay, I'll
week
look at it. Okay, is it a follow-up?
Yes, sir.
Okay. I'll look at it.
Thank you, sir.
Okay. Yeah. All right then. Thanks everyone. Thanks for joining. We'll see you on Saturday.
Thank you, sir.
Thank you, sir.